Hi, today we're going to be looking at what we call the p-series test for convergence and divergence. Now, where a p-series comes from, it comes from just an expression like if we have something like 1 over n to the p, where p is a power. And I can have numerous examples like 1 over n to the first, which is called what we call the power harmonic series, 1 over n squared. Anything where we have this power here, or what we call a p-series. So, and remember it's a series, so we're just going to be adding them up. Like if I let n be just being p, 1 over 1 to the p, the next term is 2, 1 over 2 to the p, and it could be like 1 over 1 squared, 1 over 2 squared, 1 over 3 squared. And we want to find out if this converges or diverges. Well, to do this, we're going to use the integral test to kind of show how we can use the p-series. So, we have this expression, they're saying let p be 1. So we're going to have this as n goes from 1 to infinity, 1 over n to the first. Well, if I try the nth term test, it fails, we get 0. So we're going to use our integral test. We let f of x equal 1 over x, and we know f is positive, it is continuous, and it is decreasing for all x is greater than 1. So we're going to use the integral test here from 1 to infinity, and we're going to go from 1 over x dx. First, recognize that it is indeed improper, so we go from b goes to infinity, from 1 to b, 1 over x dx. Now we can take the antiderivative. We get the limit as b goes to infinity from 1 to b, and this becomes a natural log of x. Now right away we can kind of see what's going to happen here. We're going to get the limit as b goes to infinity of the natural log of b minus the natural log of 1, which is just 0. But if I plug infinity in for b, natural log of infinity just shoots off to infinity. So I know if p is 1, this series will diverge. And that is because the integral diverges. And we write it out. The integral diverges. Therefore, the series diverges by the integral test. Well, will it always diverge? Well, let's take a look. Let's let p equal 2 this time. And I do the same thing. N equals 1 to infinity, 1 over n squared. Again, if I try the nth term test fails here. So we have to use the integral test. Let f of x equal 1 over x squared. We know that f is indeed positive, continuous, and it is decreasing for all x is greater than 1. So applying the integral test, we're going to, again, I can kind of take a little bit of a shortcut. I know it's going to be improper. So from limit as b goes to infinity, from 1 to b, 1 over x squared dx. And if I integrate this, we get the limit as b goes to infinity from 1 to b. This just becomes negative 1 over x. Notice the difference. I don't get natural log, I get 1 over x. So when I use my FTC here, the limit as b goes to infinity, we get negative 1 over b. This becomes plus minus a negative, plug in the 1, plus 1. Now, as b goes to infinity this time, this goes to 0, so I'm left with a 1. Now remember, we're not saying we converge to 1, but what this tells me is that the integral converges. Now, if the integral here converges, that tells me that the series also converges. So the interval converges, therefore the series converges by the integral test. Interesting. So when p was 1, we diverged. When p is 2, it converges. Well, what happens if we use like a fraction, like p equals 1/2 here? What do we think is going to happen? I don't know. Well, let's find out. Again, I write it out. N equals 1 to infinity, 1 over n to the 1/2. Again, nth term will fail here. So I have to use integral test. Let f of x equal 1 over x to the 1/2. F is positive, continuous, and decreasing for x greater than 1. So I'm going to use my integral test here. So I take the integral. Again, I know it's going to be improper, so I can go and set that up from 1 to infinity. 1 over x to the 1/2 dx. Whoops, make that a b though, because we already fixed the improper. So if we integrate this now, we get the limit as b goes to infinity, and this becomes 2x to the 1/2. Be careful, because remember this was x to the negative 1/2, right? Which becomes x to the 1/2 times 2, right? So that's how I get my integral here. And oh, look at this. I don't know what that is. This is a scratch out. Look what's going to happen here. I can kind of predict it. If I plug in b now, that goes to infinity. But let's see what happens. From 1 to b, the limit as b goes to infinity, to b or not to b, minus plug in the 1, minus 2. If we plug it in, we're going to get infinity. Right there. So, wow, when it's 1/2, it diverges. So we know that the integral here diverges. Therefore, the series diverges by the integral test. A lot of writing. Now, these are all what we call special cases, or what we call the p-series. Now, what makes these converge and diverge? It depends on what the power is, as you can tell. When p was 1, we said it diverges, which we called earlier harmonic series, so all harmonic series diverge. When p is 2, it converged. When p is 1/2, it diverges again. So here's what the rules that we have. If in our power series, it has to be written in this form, 1 over n to the p. We call this a p series. If it's 1 over n to the p, here's what we say. If p equals 1, the series diverges. If p is less than 1 but greater than 0, the series diverges. But if p is greater than 1, not 2, but 1, the series converges. And that's our rule for this. So take a minute if you want to. I have an example down here. And let's see what happens. Pause it if you want to. And we're back. N equals 1 to infinity, right? I'm going to rewrite this using my power rule. This is just, remember, n times n to the 1/2, or 1 over n to the 3/2. That's my p right there. There's p. P is 3/2, which is bigger than 1. And according to my rule, this series will converge. We don't have to do the integral test here. You can if you want to, but the p series is just a kind of a shortcut special case for a certain integral test. So the series converges by the p series test. And there's our answer. Alright. Hope you guys had fun. I know I did. I'll see you guys later. Bye-bye.